Hello, Longhorns. Today we're going to talk about inelastic equations. We've made it all the way to lesson number 5 in our journey through momentum. We've talked about momentum, the relation it has with impulse, which is when we consider force and time. We've also talked about conservation of momentum. Whatever I start with is also what I'm going to end with. We brought in Newton's laws, both the second and the third law, and you'll see bits and pieces of that throughout today's lecture. When it comes to an inelastic equation, the first thing I would like to do is to make sure we all have a very clear definition of what we're looking at. Your inelastic collision, is when objects collide and deform or stick together. Think about it. You've been driving down the interstate or the street before, and you notice two cars that are getting a little bit too close. If they happen to get into an accident together, let's say one is traveling north, the other one was traveling south. They're coming toward one another at a pretty nice rate of speed. Whomever has the most momentum after they stick together is going to win. So, car A, car B, they come close together and collide, and then they stick and move away. Inelastic, without elasticity. So related to your rubber band, there's no bouncing, everybody's stuck together. In these type of situations, heat is generated. It's also one of the reasons that a fire can follow after you have an accident. Between the fluids that are there and the heat that was just generated by the collision, it's a perfect firestorm for something else to go wrong. We're also going to talk about kinetic energy not being conserved. So in this example, what I start with may not be exactly what I end with either. You're going to have several examples that show crash cars. Crash cars are a really good way for us to make sure you're able to visualize what is taking place. We have our first vehicle, which has a velocity of 0 meters per second. Anything that is at rest, remember, does not have momentum. Our second crash car is traveling toward the first crash car. In the second example, they finally make contact and now they're going to move off or proceed in the direction of movement from the very beginning. Let me give you another example of what that can look like. We can also use train cars as our example. On the slide it says we're going to start with less mass and we end up with more mass. That is the exact opposite of what conservation is all about. So, where does that extra mass come from? Because what you start with is what you should end with, right? Not necessarily. So let's take a look. Let's say I have a train car that has a mass of 5,000 kilograms. And I have a second train car that is not loaded that has a mass of 3,000 kilograms. If these two cars collide with one another, in the end, for this inelastic collision, we would add the masses together. 5,000 plus 3,000 would give me 8,000 total for this particular system. So, is it less than what I started with? I started with two different objects, but as they came together, you're going to add their masses together as well. Wherever we're talking about calculating conservation of momentum, here's our equation. We have the mass of the first object multiplied by its velocity plus the mass of the second object multiplied by its velocity. This entire side of your equation is going to occur before the collision. Think about your equal sign as a way of saying these two items have finally come together. We have the mass, which will now be added together because they're stuck in an inelastic collision. And of course, that velocity is still hanging out. Before the collision, two separate objects. But after your collision, we're going to treat them as though they are one united object. Here's our problem that we're going to consider in this particular video. We have a 6-kilogram fish that swims toward and swallows a 2-kilogram fish that is at rest. If the larger fish swims at 1 meter per second, what is its velocity immediately after lunch? Pretty good question, huh? Let's see. Would you like to be the big fish or the small fish? I think most of us would agree this one is going to win out. What method should we use in order to solve this type of problem? The problems are getting a little bit longer, a little bit trickier. So let's use the guess method. First step of my guess method, of course, is the given. Take a look at your problem. Consider a 6-kilogram fish. That's a mass. How do you know? Because it's measured in kilograms. This fish swims toward and swallows a 2-kilogram fish. So that's my second mass. The 2-kilogram fish is at rest. That's one of our key words that will lead us back to our velocity. So the velocity of that second fish is 0 meters per second. If the larger fish swims at 1 meter per second, what is its velocity immediately after lunch? So what's our unknown? Velocity immediately after lunch. We're looking for that V final, which normally they're going to label just with a 2. These 2 are my initial. It's what the fish was doing before the collision ever took place. What we're looking for is that V2, or what I'm going to call V final, which took place after the little fish had been swallowed. Our equation is one that we will remember over time. M1 V1 plus M2 V2 equals, adding your masses, and of course, your V2 or V final. Now, our next step is substitution. We're going to double check that all of our units are in standard units. We have kilograms and meters per second. Are we good? I'll say we are. From here, since there's nothing for us to convert, let's move over to our solve step. We're going to fill this in little by little. Mass of our first object. So M1, which is 6, V1, which is 1 meter per second, plus the mass of the second fish, which was 2, the velocity of the second fish, he was at rest. There was a collision. We're now going to add our masses, and we are looking for the final velocity after lunch was all over. Let's multiply. Be careful to figure out or pay attention to when to multiply and also when to add. 6 times 1 will give you 6. 2 times 0 is 0. 6 plus 2 gives me 8. And then I have my final velocity. We want to simplify this just a little bit. 6 plus 0 gives me 6. And of course, that brings me here. Now, this is a tricky part, so pay attention. Between the 8 and the final velocity, right now they are multiplying. In order to move the 8, because the velocity has to be on the side by itself, we will do the opposite. The opposite of multiplying, of course, is to divide. Whatever we do on one side, don't forget you have to do on the opposite side. So we're going to divide both sides by 8. 8 on top, 8 on bottom. Those are going to cancel out. 6 divided by 8 will give me 0.75 meters per second. And that's going to be the final velocity that we've been looking for. One thing that you may notice, the initial velocity of the big fish was 1 meter per second. But the big fish final velocity was 0.75 meters per second. Was the kinetic energy conserved? The answer is no. All right? So, your given information is laid out for you. You have to be very careful to label M1, M2, V1, and V2. Make sure you pay attention to whether it is your initial or your final velocity that you're dealing with. That can definitely impact the answer that you come up with. After identifying your unknown, my equation should include all variables from my given and unknown. We're going to double check for anything that needs to be converted, and from there, you should be able to solve. Before you go, don't forget, if you have any questions, feel free to send me an email. I've also attached an additional resource